Welcome to my talk on understanding the TLS ecosystem by probing the internet. I'm Wai Tuck. I will be presenting this talk. Thank you for staying for this talk instead of looking for Python. You guys are awesome. You guys are the best.
Python is boring.
I love you guys. I promise this talk will be interesting. Hopefully more interesting than the Python one. So let's have a little introduction. Who am I? Why it's me? I do pen testing for a living. It's an actual occupation. I get to hack stuff. I get paid for that. Thank you. Yes, Mom, I actually get paid to hack. It's a good job. But in my spare time, I do a PhD part-time in machine learning. These two properties have nothing to do with this talk. This is just like something I did for fun. I just decided to scan the internet. I previously attended GeekCamp all the way back in 2014, so it has been 8 years. I'm glad to be finally giving back to the community that I really enjoyed. Some things about me, I like beer and I play CTFs. Okay, so let me give a rough structure to this talk. So this talk will be about these things. I need to baseline everyone so everyone knows what TLS is. Then I'll share about how I did my scan and what I screwed up on. So this is like not a perfect scan. Reason why I'm sharing this? The reason why I'm sharing this is because, well, I guess it's hanging. That's not what it wants to do. Technical difficulties. I may be getting hacked. It's okay. We have technical experts here in this room, which is everyone. Thank you for coming. Okay, yeah. So I did the scan. There are some things wrong with the scan. I'll talk about it. You guys will know about it. And then you guys would know that these are things not to do and what are the things to do. But I did collate some interesting results. We actually collected over 9 million certificates from the scan. I did some data analysis. I'll talk about some of the things that we see in the internet now. And it's actually representative of what industry scans have been actually reporting. I share some of the trends, and I conclude this talk by sharing with you why this ecosystem is so weird. Okay, so level setting the audience. What is TLS? I'm not going to go through like the entire TLS handshake because everyone will be bored to death. Okay, no OSI either. But we'll be basically looking at what the average person knows as TLS, right? You go to a website, your bank, Google, you see this green lock, and this is essentially what TLS is. Of course, what does it actually represent? What does it actually give you? And just to illustrate the process of what it looks like, let's say you're Alice, you're trying to communicate with your bank. Maybe you want to invest all your money in Dogecoin, that's the thing that you like. But you don't want people to know about your preference for Dogecoins. So you want your traffic to be in the secret tunnel. And essentially, TLS provides us that. And adversaries, like this man right here, will see just rubbish. And that's a very simplified view of what TLS is. We'll go a little bit deeper now into the properties that it actually provides. So firstly, let's say on the internet, you are trying to log in. You need your username and password, right? So by default, on the internet, if you don't use TLS or you don't have the HTTPS lock, you essentially are passing your username and password in clear text. Your ISP, your neighbor, if you're on public Wi-Fi, will be able to see your username and password. And obviously, you don't want your neighbor to know that Bob is your oppa. So the TSL tunnel provides this protection that prevents anyone from knowing what you're sending across the internet. So your ISPs don't know what your password is, which is good. You don't want your ISPs to know your password. Another property it provides is integrity. What integrity actually means is that whatever transactions that you made on the internet, you want to make sure that you click that button, it is what you think it is doing. So let's say you make a transaction to sell 100 Bitcoin. You don't want it to suddenly change to something else. You don't want this malicious fella to suddenly, buy 100 Bitcoin when it's already falling by a lot. And so TLS provides the guarantee that anything, if it was tampered with, if the traffic was tampered with, essentially the other party will actually know and then reject that traffic. Finally, the last property that TLS provides us is authenticity. So how the internet works is that you need to be able to navigate to a website, but where is the website hosted? So where is google.com hosted? You need to talk to a DNS to resolve an IP address so that your computer knows where to route that packet, and you can talk to your bank or whatever service that you want to use. So you would ask the DNS server very nicely, hey, I want to visit bank.com. The DNS server would give you back an IP address. This is not a valid IP address in case someone tries to visit. And then you will make the request directly to the bank. But how do you know that this thing is destined for the bank and that the bank is the one talking to you? You actually don't know that for sure. Someone could be in the middle and say, hey, I'm actually the bank. What's up? And you're kind of screwed. So if you have TLS, what actually happens is that you have the same process. You ask the DNS nicely. They give you an IP address. You talk to the IP address, and this protocol actually defines a way for the bank to prove that it is the bank. And this proof, right, cannot be reproduced by someone that is evil because they don't have that secret that the bank only has. So just to recap, this is pretty important properties of TLS that this protocol provides. It provides us with confidentiality, integrity, and authenticity. So TLS is pretty important for the internet. If you don't have this, like, how do you even trust what you do on the internet, right? People can just change what you do. They can see your password. They can see what you're doing. That's not. So it is a very key cornerstone of the internet. But with all that, right, it's like all beautiful, it's like the most magical protocol, but there's actually a lot of weird things that happen in this ecosystem. And the world isn't all sunshine and rainbows, right? And to understand what's really happening under the hood, we actually have to dive deeper. So that's the superficial background that we have to go through. Everyone knows what TLS is. Now we have to go into a bit more technical detail. I promise not too much. So there's a very technical diagram there. It's the simplest technical diagram I could find. But we're not going to talk about too much about this. But essentially what we have to know here is when we talk to a service like Google or your bank, they actually provide us with a certificate. That certificate has a public key that allows us to encrypt our communications to the server. And there's some symmetric crypto as well there. And to prove that we are talking to the bank, we can actually check whether the certificate is actually issued by a trusted third party. How we do that is that there's a bunch of things in our operating system that essentially it forms the trusted store. So these are the certificate authorities, the people that distribute the certificates. They actually provide their information, and we are able to use that information to verify that the certificate is indeed issued by someone that's trusted, so we can trust that the certificate is actually issued by someone that is trusted. And then with that, we can actually trust the server, because if they prove that they have the private key that's associated with the public key, then we know that they are who they are. And the adversary won't have the private key, and this is essentially the cryptographic primitives, or TLS, in a nutshell. Of course, in the middle, they decide what cryptographic protocol they want to use to talk to each other. And this actually differs by version, right? Because every few years, crypto is broken, MD5 is broken, SHA-1 is broken, SHA-256, it hasn't broken yet, but who knows? So different versions ship with different cryptographic protocols, and all these things actually have some issues related to this. So because of all these core primitives that are being used, there are problems that actually plague TLS. So back in 2011, remember I talked about this trusted store. So who checks that this trusted store is a trusted third party? They can sometimes be compromised, and this is actually a case. And this is very recent, like just 10 years back. So a trusted certificate authority was actually compromised and was used to create a fake certificate for Google. So that adversary was able to impersonate as Google. So all the properties that we talked about earlier, confidentiality, integrity, authenticity, all out of the window just because one certificate authority was compromised. And not just that, right? We'll talk about the cipher suites that are negotiated. There's a huge historical baggage that comes with TLS. So it goes all the way back to SSL version 1 to version 2, version 3, then TLS 1.0, 1.1, 1.2, 1.3. Sometimes you need backward compatibility because you want to support more customers, and maybe that's not a good thing. So it's a really quite a painful history in TLS because there is a history because essentially every upgrade is a fix of a previously of a vulnerability that was found in a previous version. So in recent history, there are attacks on CBC. If you went to the crypto talk just now, CBC padding Oracle has been exploited to death in TLS, and in fact, it is. You will find out that later it's completely removed in the latest specifications. There are also compression side channels, where if you compress plain text, you can use the length as a side channel to actually find out what is the content of the plain text. RC4 is broken. That was the previous stream cipher that was used in TLS. And there were additional implementation issues because coders make mistakes. Everyone makes mistakes. And even the specs has mistakes. So as you can see, version 1 is missing from this timeline because it was never released because it was too broken. So that's a great start. But version 2 is deprecated in 2011, version 3 in 2015, and in version 1.1 and 1.2, because they supported roughly the same ciphers, they were deprecated around the same time. So currently, we are at a state where we have TLS version 1.2 and 1.3, which have support for ciphers that can be used in a safe way. And TLS 1.3 is this new specification, right? This new exciting specification that promises to solve all our problems in TLS. It adds like magical new stream ciphers called Cha-Cha-20. They prohibit the use of all the broken stuff that was implemented in the past, which is like finally, right? They make things super fast because they allow, instead of your typical handshake, which takes like, I don't know, 3 round trip, they promise like, hey, you can do it in 1 round trip time right now. And they drop all the, I wouldn't say useless features, obsolete features that were actually harmful for the ecosystem. But you have a new release, but who's going to upgrade, right? And how long does it take for them to upgrade? We actually don't know this. So I sought out to actually try to figure out what is the real adoption of this on the internet. So in this next section, I'll talk about descan. So before you even start scanning, right, you have to think about this. If I do this, why go to jail? It's an important question because I'm also bonded, so I'll have to pay damages. But other than that fact, let's see what other people have done already in this space. So the EFF has actually done the first worldwide HTTPS scan in this project called the SSL Observatory. So no one went to jail there, so that's great. In 2016, someone scanned the entire IPv6 internet. I think all of them are still alive and not in jail. Someone scanned a different service for robotic research, and there's actually paid commercial services that provide this data called Shodan. And so it seems like if we are doing it for science, it should be fine. But again, I'm not a lawyer. Don't quote me on this. If you choose to do this, right, my PSA here is don't try this at home. It's the same as what they propose on WWE. Of course, no one follows that, but yeah, don't try this at home. And there's actually real ramifications behind this. So there was an internet scan that was done in 2015, and that person that scanned it, or that organization that scanned it, actually received 12 active hostile responses. So what does it mean by hostile responses? So A, they were actually sued by other organizations. And secondly, or at least threatened to be sued by other organizations. And secondly, there were actually hosts that actually try to have retaliatory DOS traffic, denial of service traffic. Essentially, they flood your device with traffic so that as a form of revenge. So don't do this on your machine. Obviously, don't do this at home unless you want your whole Wi-Fi to go down. And also, these kind of scans actually trigger intrusion detection systems because you're scanning the whole subnet, right? And people will see this IP is scanning my subnet range, and maybe your organization is Google. So you're like, what is this guy doing, right? Well, can I find out who this guy is? And if they're lazy to find out who you are, they may just block your IP address, and then you'll never be able to access Google again. So your mileage may vary. You take your own risks, YOLO, etc. So now that you are mentally prepared to take the legal risk, you start to look for instructions online, right? Because like Google is your best friend. You'll find this article like how to scan the internet in 5 minutes, and you open it and it's like a scam because they teach you how to use Nmap, which is not what you need. But then you encounter this software called Nmap on GitHub, which claims to be able to scan the entire internet space in under 45 minutes, which is about the length of this talk. So imagine if you start scanning now, maybe you can finish by the time you finish. So it says like, oh, it's either 45 minutes or 5 minutes. This is like, so when I first read this, right, I thought, this is gonna be easy, man. I'm gonna be finishing this in like a day, collate the results, write the talk. But unfortunately, there's a extrapolation right here. So there are a lot of factors that come into play in scanning. You can't just scan 3 hosts and then expect that to that kind of performance for the entire internet, for example. And you can't expect to have like an increase in one wife or one husband and expect to have more husbands and wives. Trust me. So there are lots to think about in scanning. I'm just going to list some of the factors or things that you think you have to think about here. So firstly, you want to scan fast, right? You want to utilize all the threads that you have on your machine, all the cores, that you spend on your expensive machine. But for every thread that you have, you realize that it's a connection. A connection is also a file. And I hope that you configure your Mac's open file handles correctly, because if you don't, you may start getting errors, and then you have non-reliable scans. Next, you're scanning the internet. The internet is worldwide. The world is very big, in case you didn't know. It takes 16 hours to fly to the US. But of course, your packets will take a lot shorter time, but you have to think about how much timeout do you actually need, right? If you want to get reliable scans, you need long timeouts. But if your timeouts are too long, then you're going to wait forever for the scan to finish. Then I cannot give this talk. And even if you decide, hey, let me fix this timeout value at this number, let's say it times out. Do you retry? And if you do retry, how many times do you retry? Because each time you retry, it's a factor of increase for the time that it takes for you to scan. And there are a lot of hosts which are not accessible, so you're actually increasing your time by a lot. And you need high bandwidth. Unfortunately, local ISPs cannot give you the bandwidth that you need to do this kind of scanning quickly. So you have to utilize something in space or in the cloud, whatever. And TLS handshakes are actually way more expensive than the typical kind of scannings that Nmap reports or whatever scanning speed records. Which is usually a ping scan or a SYN scan, which is just like the first part of the TCP handshake. For a TLS handshake to be established, you need to have the TCP handshake, which is your SYN, ACK. And then you also need to have the TLS handshake, which, depending on the version, can be 1 round-trip time or 2 round-trip time. It's roughly about 3 round-trip times in total. And of course, when you're actually doing this, there's actually computational costs as well, because there's cryptography involved, and some computers are slower than others. You don't want to be doing this at home literally, because legal ramifications, potentially being blocked from the internet, that's probably not good. So when you are faced with all these variables, right, the thing you should do is just do it, because just try to start with a initialization for the variables and see what happens, and then just iterate until you find a good fit for the parameters. That's like machine learning anyway. So now that we have a way of thinking about our scanning, we need to define what we actually want to scan, right? And of course, we're scanning the internet right here. Isn't that simple? Just scan the internet, right? What does the internet mean to you guys? Is it just a number? Or is it more than a number? Because I can start scanning from the whole IPv4 space. Maybe I focus on 443 because that's where all the HTTPS servers are. And I can scan from the whole range, right? Of course, I am simplifying here. You obviously omit some ranges because they are not valid IP address ranges. But 2 to the 32 is a huge number. It's approximately about the number of humans that have ever lived in this entire world, minus a few billion. And that's a lot of humans, if you think about it. But then that's a lot of hosts. That's my point. And does anyone see anything wrong with this sort of formulation, to just scan the internet looking at IPv4 addresses? Of course, that's a rhetorical question. I don't expect you to know. But you see that my results of 9 million hosts seems a bit little, you know. Like, there should be more internet websites in the world than 9 million, right? So I have to admit here, I messed up a little bit. Just a little bit. And what you come to realize is that, and this is obvious, like, when you think about it retrospectively, but at that point of time, I was like, oh, yikes. Different websites can have the same IP addresses. This is like, whoa, yikes. So I'll give an example from our favorite website in the world, which is Stack Overflow and superuser.com. Everyone visits those sites. If you dig for their IP addresses, they have the same IP address. I bet you didn't know that. I didn't know that before this talk either. But if you actually visit the sites, right, they actually present you with 2 different sites. So what's actually happening behind the background? Magic, sort of. It's a concept called virtual hosting, or related concept is called domain fronting. But essentially, because in that TLS handshake, what happens is that the client will actually request for a particular server. In this case, the server name is included there. And on the back end, right, it actually routes and serves different responses based on the server name. So this is actually what's happening in the background. And by scanning IP addresses, we are actually not capturing all these different backends that are not accessible via IP. So that was a little mistake, but it's also just happy little accident. It's fine. It's not for production use anyway. So just to recap, the internet is not just IP addresses and ports, but you also have to think about domain names. Now, the real question is, how do you actually get all the domain names in the world? You can't. You can't just go to a DNS server, knock on their door, say, hey, just give me all your DNS records, A records, easy. If you do manage to do that, please call me. I would like to know your name. Or you can try to ask someone that knows, maybe Google. But here we are going to take an approach called approximation. Since we can't really get all the domain names from a DNS server, we can try to get as many as possible. And there are actually 2 data sources that we can actually get this from. I'm going to caveat this and say that this is left as an exercise for the viewer, because I did not actually use these data sources for this scan. But you can actually look at the certificate transparency logs. So when you actually register for a certificate now, you actually have to push your certificate to a certificate transparency log. So websites will have their certificates on this particular database. You can search it up. The issue with this is that you register it, but what if you don't use the certificate? Then it's actually not hosting anything, right? It's not hosted on the internet. So there can be false positives there. So you want actual concrete things that you can hit on the internet. So that's where the common crawl dataset comes in, where it crawls the internet for hosts, and you can see what's and essentially it collects all the domain names that can be reachable from the web. And These are two very good data sources for domains. And just to give a sense of how much we're missing just by only scanning IP addresses, this is from a paper to get a complete view of the certificate ecosystem. If we just do an IPv4 scan, which is what I did, you will only get 3 million out of a total of 16 million certificates. So it's essentially 75% missing. So there is a serious miss there. This probably can't be, like the work I'm doing here probably can't be published in a paper, but I can give a talk about it. So, okay, now that we have our target, we need to have a weapon of choice, right, to scan the internet. So there is Nmap and then there's Zmap. Z is lower in the alphabet than N, so we choose Zmap. Of course, that's not the real reason, but Zmap is written in Go. It's good for concurrency. It serves a different purpose in that it's for scanning, enumeration, and not for vulnerability assessments. Nmap has that vulnerability assessment component, so a bit more heavy duty. We don't need something so heavy duty right here. We will use Zmap. And in particular, we'll actually use zgrab2, which is built on top of Zmap, and it allows us to do more complicated handshakes like the TLS handshake. The caveat about this is that if you actually go online to all the data sources about scanning, you actually realize that if you look specifically for servers that only do TLS v1.3 handshakes, that they reject TLS 1.2 and below, these aggregation sites actually do not have those sites in their database because right now there is no good tooling to do TLS v1.3 scanning. So as a caveat, this tool that I show you here does not come with TLS v1.3 out of the box. You have to do some tricks to make it work. I'll leave this as an exercise for the viewer. So you have the tools. Now you need to make sure that you don't blow your wallet trying to do this, and you don't have to wait forever. So I just did a small experiment on 200,000 hosts, and this is the average time to scan. So 17 seconds for 2 to the 16 hosts, and maybe 30 megabytes for 2 to the 16 hosts, because we're actually storing the certificates. And if we were to scan the whole IPv4 space, it will take 300 hours and 2.1 terabytes using our Scratch calculations here. In reality, it's much less space, but it's about the same amount of compute hours. But to deal with this number of compute hours, what we can do is just spin more instances because we have the cloud. So that's what we'll do. So once we have that, right, all we have to do is just bootstrap the input into an EC2 instance and create our own hacker ETL pipeline because like hacker. And then we just have to repeat for all /8 subnets. We dump the result as a JSON, and then we just send the file over to OpenSearch. This post is not sponsored by AWS. So in posting that file, right, imagine you have so many hosts. Like, what could actually go wrong here? So the file is actually really huge. You can have 10 gigabytes worth of data per file. And so you have to do some buffered reads, and that's just an aside. Cool, let's look at the results. This is going to be quite short. So this is the number of hosts we scanned, 9 million. We ingested 96 gigabytes. We collected these amount of certificates. There are 5 million certificates. There were 300,000 expired, 900,000 self-signed. The satisfaction in scanning is priceless. I didn't go to jail. That's also priceless. And this data was actually gathered in March 2022, which is quite recent. So if we look at the 5 million valid certificates that we have, we actually didn't do that bad of a job. I think I did pretty decently. I had more than what they scanned in 2010, which is expected because of the HTTPS adoption. So that's nice. So what we are interested in is the adoption of the newer specs, the TLS v1.2 and 1.3. So this graph shows like the aggregated data of the different ciphers that are supported in the different hosts. This is the maximum level of TLS that they can support for those hosts that were scanned. So this TLS v1.2 is an aggregation of both 1.2 and 1.3 because of some issues in the underlying application of my scanner. But essentially, there are 98% or 8 million sites that actually use non-deprecated TLS. That's a great thing. Yeah. But we want to zoom in into specifically TLS v1.3. And to do that, we just have to simply look at the cipher suites that were established or agreed upon by the server and the client. And for TLS v1.3, there are specific cipher suites that are supported only in that version. But before I go into that, I forgot the slide. Essentially, why is there so much support for TLS v1.2 and 1.3? There's two main reasons. A, if you go to your browser and you try to visit anything that has TLS 1.1, 1.0 and below, it's going to say, I don't want to view this, this is bad. The second is there's also a huge industry push from PCI compliance, etc., to say, hey, don't use this version anymore, otherwise you won't be compliant. So that's nice. But specifically TLS v1.3, we actually have a pretty decent number. So the TLS 1.3 ones are the ones with Cha-Cha, Poly 1305. Those are the TLS v1.3 cipher suites. And we see that actually the biggest green part, which is Cha-Cha 20, Poly 1305, the TLS 1.3 ciphers are actually the top cipher suites negotiated. And from the scan of the entire internet, not just Alexa 1 million, we find that 52% actually support TLS v1.3. So that's okay, I guess, but you have to realize that this standard has been out for 4 years and it's only 50%. It's okay, but also like it's not too bad. But what I'm really happy about is that we are actually able to confirm the official estimates from SSL Labs. So they estimated 54.2%. We got a number that was quite close. So we confirmed their results independently. So that's pretty cool. And when you do all the scanning, right, you encounter very weird certificates. So this is a certificate with a very interesting parameter. So if you do RSA, you usually have to pick two numbers, n, which is like a factor of product of two primes, and e. So can anyone tell me what's wrong with this e right here? So this e, right, is not your very standard e. E is usually 65537, a much larger number. With a number like 3, you can actually just take the cube root of like whatever message that you exponentiate to. So this is like a horrible parameter to be used in RSA. But what do you guys think? Is this a valid certificate that's accepted by your browser? The answer is yes. And the exciting thing is there's more than one site like this. What gave them the idea that this is an acceptable parameter? I don't know. I don't work for any CA. If you work in a CA, please let me know why this happens. So there are a lot of weird things that happen. Of course, you see that some sites on the internet still use SSL v3, which is insane because this is like 4 versions below like what is the current standard. So what's actually happening there? Right? What is on this like wild west of the internet? Like what services are actually hosted there? So some of it is like innocuous services, like this house right here. I don't know what this is. If you understand this language, please let me know what this is. I think it's for some house. But you also see some interesting things that you probably don't want to see, like security system. And that's when I knew I had probably had to stop, so I didn't put more websites here. So yeah, I don't want to go to jail. So closing thoughts. So the problem with OpenSSL, all these TLS implementations is that, let's say you have a problem in the library itself. For example, the alpaca attack, which is an implementation issue. It's quite recent, happened in the past year. what actually happened was that you needed to update a lot of things, right? Even in their official disclosure, they say, oh, you know, this bug is not simple. You think you can just fix the library and you can fix the bug. That's not true. You actually have to fix all the other, you have to fix the clients, you have to fix the servers so that they agree upon that standard. It's pretty insane. And recently there is this news on November 1st, I believe, OpenSSL will tell you you have to upgrade to this version, otherwise you are vulnerable to this, some vulnerability. So I don't know if anyone here has tried to upgrade OpenSSL, or like you have to do this across an entire organization, but it is extremely, extremely painful. Because a lot of code depends on OpenSSL. If you make a connection to the internet, you probably depend on OpenSSL. This is like mostly fine because usually if it's a security fix, there's no functional differences. You can just upgrade. But if you're dealing with legacy code and somehow the fix is not backported, now you have an issue. And not only do you have to update your own code, you have to update the dependencies as well. And you probably have a lot of dependencies that depend on OpenSSL. And you need to wait for the vendor to ship the fix, and it's a very sad situation, right? So you don't want that to happen. Is there a better way of fixing this dependency hell? I don't know. And of course, there is this interplay between clients and servers as well, because clients have the ability to reject poor standards in communications, right? And this is something that is two-sided. Servers have to upgrade, but clients, ourselves, we have to upgrade as well. Finally, let's talk about centralization versus decentralization. So certificates are becoming increasingly centralized. A lot of people are using certificates from Let's Encrypt. The good thing about this is that you have standardized parameters, you have a reduced likelihood of expiry, and people adopt TLS. That's all very nice. But let's say the root certificate is compromised. What happens to all these other leaf certificates? Will the internet go down? I don't know. I hope that never happens. Anyway, I know I'm coming to the end of my talk, so this is the end of my talk. I'm happy to take any questions. Yes?
So when you come to the field of cybersecurity, right? So how was it when you came new to the cybersecurity field and hacking stuff?
When I was new to the cybersecurity world, I guess I've always been immersed from young. So like played with cheat engine, the memory, changing values in memory. So I guess I don't have the best context to answer this, but I guess I always was interested in this kind of thing. And like, I mean, this is not really cybersecurity, but like I think security itself is exciting stuff because it forces you to understand how all components interact, and you want to find the weakest link and how to chain multiple different vulnerabilities together to actually get something that you can actually exploit. I think that's really quite fun. It's like a puzzle. Yeah. So I will take more questions because I have 4 minutes.
3.5.
Okay, I have 3.5 minutes. So
Any more questions from the audience? If not, this is going to be a one-to-one.
yes.
Hey, Sam too.
What was the weirdest website you discovered?
What was the weirdest website I discovered?
Besides the CCTV.
This is so. I guess some of the weird websites is not really like I wouldn't talk about the content, but I'll talk about the private keys they were using, right? So I think in a previous talk, Jules actually talked about Hyundai using sample keys. There were actually many sites. I mean, some sites were using sample keys from like some Kubernetes repository on GitHub, and they were hosting that site using those sample keys. So like people take that sample key a bit too far, and they were hosted on legitimate domain names as well. So it's a bit scary, yeah, the way people use TLS or set up their servers.
So what's the final end percentage of websites that are somehow still on SSL 3?
And percentage, it's less than like 0.01%. There's only like a handful, like 300, 400 websites. Of course, this is not an exhaustive scan. I think I want to caveat that because like to get reliable TLS scans is actually very difficult.
As
that
you've
was also part of
mentioned,
the messaging.
all the
Yeah,
timeout retries.
yeah, exactly.
All right, thank you, Wai Tuck. Can we give him a round of applause one more time?